When we supply power to the Mitsubishi inverter mini-split air conditioner, you can see that the green light turns on, which is the run light. After waiting for some time, the timer light starts blinking. Now, if we count the blinks, 1, 2, 3, 4, 5, and 6, it blinks 6 times. This indicates a serial communication problem, meaning that either the indoor or outdoor circuit board could be faulty, or both might have issues. To address this, there are 2 methods we can use. The first method is something that anyone can do, even if they don't have prior knowledge of the issue, and it can also be commonly used by technicians. However, there can still be a problem with this method, as I experienced. Let me show you. When I turned on the unit, I will check the terminals of the connectors. I will check on the neutral wire and the 3-number wire on the connector in the indoor circuit board. I'm checking it in DC mode. As you can see here, there is some voltage fluctuation. If the circuit board isn't showing an error, it means the communication is fine. But in my case, the communication seems somewhat okay, which means we can say that the circuit boards are fine and communication is happening. But despite that, there's still a problem. This indicates that there might be an issue with one or both of the circuit boards causing the fluctuation, but still leading to a serial communication problem. Now, this is the normal method of checking with a multimeter, but since we're seeing fluctuation here, the problem still exists. So we'll use the second method, checking with an oscilloscope or DSO. Whether indoor or outdoor PCB, circuits are designed to detect serial communication. In the indoor PCB, you'll find a circuit here with 2 optocouplers, IC11 and IC12, along with some diodes and a PTC sensor. Similarly, in the outdoor PCB, there are also 2 optocouplers, a diode, and a PTC sensor installed, which is red in color. In the indoor PCB, as I showed you, IC11 and IC12 are installed. These optocouplers are responsible for receiving and sending data. One of the optocouplers receives data, which is known as RX, receiver, and the other sends data, which is known as TX, transmitter. Now, let's identify which one of these, IC11 or IC12, is the data receiver and which is the sender. We'll understand this in a very simple way. First, you need to observe which optocoupler is facing the communication wire. As you can see, IC12 is oriented towards the wire. This means that IC12 is always the RX for the indoor PCB, meaning it is the optocoupler responsible for receiving data. Similarly, the optocoupler that faces away from the communication wire is responsible for data transmission. If you observe, IC11 is oriented away from the communication wire, with its pin 1 facing in the opposite direction. This indicates that IC11 always transfers data from the indoor unit to the outdoor unit, making it the TX transmitter optocoupler for the indoor PCB. To explain the data transfer process, pins 1 and 2 of the optocoupler have an emitting diode, which turns on and off in a specific pattern and frequency when voltage is applied. This on-off pattern corresponds to the data being sent between the indoor and outdoor units. A transistor is connected to the emitting side of the diode, and a certain voltage stands on the transistor's emitter side. This voltage, matching the pattern and frequency of the emitting diode, is then transferred to the microcontroller. The microcontroller interprets this pattern to understand what the indoor or outdoor unit is communicating. If you're repairing a circuit board for the first time, you will need to determine which circuit board is sending data first and which one is receiving it. This might require some additional work and troubleshooting. To start communication, brands typically assign one PCB, either the indoor or outdoor unit, the responsibility of sending the first signal or welcome message. Some companies assign this task to the indoor unit, while others assign it to the outdoor unit, depending on the brand and manufacturer. It's crucial to remember this when repairing a PCB so that you know which PCB initiates the communication. This makes the repair process easier. You get to know where to start troubleshooting. Now let's get ready to test the communication using an oscilloscope. First, we'll prepare everything. Here, we see a capacitor labeled C3, which we'll use as our ground or negative point. The ground pin is on the right side, but it will shift to the left side later. We'll attach the probe to this point, securing it firmly. Next, we'll supply power to the indoor PCB again. The PCB is on now, and IC11, which is the sender TX, is transferring data. I'll check this by placing the probe on pin 1 and setting up the oscilloscope. We can see the data flowing, though the frequency isn't showing clearly yet. To get a better view, I'll adjust the position slightly. Now, you will see the data and the frequency more clearly on the oscilloscope. The frequency is not showing properly on pin number 2 of IC11. If we need even clearer signals, we can check the transistor labeled Q1. After supplying power again, you'll notice that signals start appearing at the base pin of the transistor. These are complete signals. If we check on the other side of the resistor, we'll see fluctuations, showing a movement of around 50 Hz, with the voltage currently at -2 volts. However, the signals aren't fully clear because the pattern isn't properly formed. This indicates that the indoor unit is generating signals. For the outdoor unit, we need to work quickly because if the indoor unit stops generating signals, it will be difficult to check. In the outdoor unit, we first observe the red wire, which is the signal wire. After that, we have ZD1, a Zener diode, followed by IC4, which is the RX receiver. For the outdoor unit, we know this because pin 1 faces the signal wire, according to the simple formula I explained earlier. This makes IC4 the RX and the other optocoupler the TX, since its pin 1 is opposite the signal wire. In this situation, the signals initially pass through the wire into the Zener diode, and then they are supposed to travel further along the circuit. However, let's observe the position by turning the PCB back on. Once powered on, we can see the signals traveling to the anode side of the Zener diode. But if we check the other side, the signals disappear, indicating that the signals are not crossing the diode. This suggests a fault in the Zener diode, potentially a short circuit. To confirm this, we'll need to properly check the Zener diode to see if it's indeed faulty. For the further test, I will use the multimeter. But before conducting any tests with a multimeter, make sure to disconnect the system from the power supply to avoid any risks. Now, let's test the Zener diode with a multimeter. Currently, there's no reading, so let's switch the probes. With the anode on one side and the cathode on the other, the multimeter should show a value. It reads a 0.627 voltage drop, which indicates that the Zener diode is functioning correctly according to the multimeter. However, it does not allow the signals to pass through the circuit. The best course of action would be to replace the Zener diode. This is a 1 watt and 24 volt Zener diode, and I will replace it with one of the same specifications. In the same circuit, there are additional components, including resistors and capacitors, that also need to be checked. Among the resistors, there is a 47 ohm resistor, a 1 kilo ohm resistor, and another 1 kilo ohm resistor labeled R27. I will set the multimeter to ohms mode. The 47 ohm resistor shows a value of 09.47 kilo ohms, which is much higher than expected. This discrepancy suggests a potential problem with the resistor, though it's worth noting that testing components while they are still in the circuit can sometimes yield inaccurate readings. To obtain an accurate measurement, you'll need to remove this resistor from the circuit and test it again. On the other hand, the 1 kilo ohm resistors, including R27, are showing correct values, indicating they are functioning properly. The incorrect reading on the 47 ohm resistor indicates it might be faulty. A resistor that shows a higher value than its rated resistance can cause issues in the circuit, such as improper data transmission, leading to malfunctions. To resolve this, I will remove the 47 ohm resistor from the circuit and test it again. After removing the resistor from the circuit, I'll check its value independently. Upon testing, the resistor shows a value of approximately 63.6 kilo ohms, which is far from the expected 47 ohms. This suggests that the resistor might indeed be faulty, so I'll replace it and then reassess the situation. I've prepared a new 47 ohm resistor to replace the faulty one. Now I will solder this new resistor over here. After soldering the new resistor in place, I'll check its value again. The new resistor shows a value of around 47.4 ohms, which is within the expected range. However, to confirm that this resolves the issue, I'll need to test the circuit. Now that I have set up the entire system again, I am going to connect the power. I've connected the power and I'm turning it on now. Look, the light has turned on. We'll wait a bit now. There are two types of errors showing up. First, the yellow light started blinking, and now the green light has started blinking. It's blinking 1, 2, 3, 4, 5, 6 times. This light is also blinking 6 times. So this could be a problem with the indoor fan motor because we don't have an indoor fan installed. Now remember one thing, never directly install a DC motor onto the PCB that has power in it. Otherwise your indoor DC motor or any circuit could get damaged immediately. For this, turn off the power. Now let's check the outdoor unit to see if the signals are coming properly or not. For that, we are using the DSO or oscilloscope again. I have turned the system on, and now we don't need to wait too long. Let's check at the emitter and collector points. So look, signals are forming at around the 50 Hz frequency. Now, look at this pin of the optocoupler. It's showing the same voltages. If I connect it to pin 1, you can see that the signals are very clear. I'm increasing the focus a bit now, and you can see the signals forming clearly. The entire pattern is forming, and the signals are coming and going at approximately 42 Hz in different patterns. You can see that on pin 1 of this optocoupler, the signals are visible at 37 Hz. Similarly, if we look in this direction, on pin 1 here as well, you can see signals forming. Here, the signals are forming at around 50 Hz, and similarly they are forming on both pins. Now look at this other optocoupler, IC5. On its pin 3, you can also see signals forming, and it seems like the signals are heading towards the indoor side. You already know where to check the signals on the multimeter. You check them on this terminal. I'll connect it to neutral and then to pin 3. Now you can see what we're getting here. The patterns have changed, which means our communication system is now working perfectly. And you saw that this entire problem in the system was caused by just one faulty resistor. Click on the left or right thumbnail to watch our next videos and subscribe. Thank you.